So let's get started with our forces and free body diagram notes. So the first thing we want to do is talk about what is a force. Well, we're going to define a force as a push or a pull on an object. Anything that pushes or pulls an object is going to generate a force. And again, right here, we can just see a picture of somebody pushing on a door and somebody pulling on a door. So this is a very simplified way of talking about what a force is able to do. So again, forces are either able to push an object or pull on an object. And again, here's just a picture demonstrating that. And I'm sure that this has all happened to us, where we try to push on the door, but it really says pull. Super embarrassing, but let's be honest, it's definitely happened once or twice. So now we want to start talking about different types of forces. The way we're going to talk about these forces, though, are first identifying what type of force it is, and then defining what that force does. So the first one we're going to talk about is friction, and friction is a contact force. What that means is that you must be in contact with an object in order for friction to exist. Friction is defined as a force that is opposite when the object slides across a surface. So for instance, if I have a box right here and it's moving to the right, so it has some velocity to the right, friction is acting on this box in the opposite direction. So I would have friction acting in the opposite direction. And friction also is just a force that slows down objects that are moving. The next force we're going to talk about is tension. And tension is also a contact force. Again, contact is just talking about the fact that this force needs to be touching an object in order for it to occur. Tension is what happens when we have a string, a rope, or a cable that is pulling on an object. So again, imagine I have this box, but again, this time I'm pulling this box with a string or a rope. Because it's a rope, this time it's tension that is acting on this box. So tension is what's pulling it. Again, tension can only be present if we have a string, a rope, or a cable. Next, we have the normal force. And again, normal force is something that can only happen when an object is touching something. Normal force is also the one that people struggle the most with. And we're going to define a normal force as a force that is exerted on an object in contact with another object. So for instance, I have my box again, but this time my box is resting on a table. So because my box is resting on an object, there's going to be a normal force. And that normal force is just a force that is pushing back on that object. So let's think about it like this. This box is pushing down on the table. Well, my table is pushing up on the box. Normal force will always point perpendicular to the surface. Next, we're going to talk about air resistance. And again, air resistance is a contact force, meaning that air has to be touching our object in order for it to exist. Air resistance is just a fancy way of saying friction in the air. Air resistance is just applied by the air, and air resistance is going to point again in the opposite direction of motion. So it's going to slow down moving objects in the air. So let's say now we have a box just like we did before, but this box is falling in the air. So because it's falling, it's going to be moving downward. So its velocity is in this direction. Therefore, air resistance is moving upward on it. Air resistance is moving in the opposite direction. Force applied is just a contact force, just like we talked about before, meaning that something needs to be touching something else in order for this force to occur. And force applied is just exactly what it sounds like. It is a force that is applied by a person or an object. If you were to push or pull any object, you are applying a force to it. But don't get confused. If you push or pull an object with a rope, yes, you're applying a force, but you're applying that force to the rope. The rope or cable is really applying that force to the object. So an applied force occurs when it is you making direct contact to that object. Next, we have force spring, and force spring is a contact force. And it's exactly what it sounds like. Force spring is just a force that is applied by a spring that is touching an object. So think about So let's think about our pen, right? If I have my pen and I push the pen down, I can feel that there's a spring in there, and I can feel some resistance on my thumb as I push that pen down. Another example of force spring would be a trampoline. When we jump on a trampoline, that trampoline has springs. When I land on the trampoline, I'm pushing those springs down, and then those springs are pushing me back up. So when the springs push me back up, it's applying a force on me, and that's allowing me to jump up and down. And the force that it applies on me is a spring force. Our last force, and this is the most important one, is going to be gravity. And gravity is the only force on our list that's going to act at a distance. And what we mean by acting at a distance, we mean that gravity does not have to be touching an object in order for it to occur. So think about that, right? If I were to throw a ball up in the air, well, the ball comes back down. Is anything touching it in the air that's bringing it down? No. Gravity is a result of the Earth. The Earth is not touching my object when it's in the air. Since gravity is so strong, it can interact with objects by not touching them. So again, like we said, we're just going to define gravity as the attraction towards the Earth. And something really, really important to note about gravity is that it will always point down. So I'm going to go ahead and highlight just a few important forces that we're going to see over and over and over again. You need to know all of these forces, but these four are going to be seen a lot more than the others. So make sure that you definitely know these four. Now let's talk about free body diagrams. A free body diagram is just a way to show magnitude. And by magnitude, we're just talking about the strength or the size of our force. And it also helps us show the direction of all those forces acting on an object in any given situation. So we're going to go ahead and show what that looks like in a sec, but just make sure that you remember that our free body diagram is used to show the forces acting on an object. Very, very important things to remember here. The size of your arrow matters, okay? So size definitely matters here. And the size of that arrow reflects the magnitude, like we said before, meaning the size of our force. So the bigger our arrow, the stronger our force is. So for instance, a big arrow might indicate 100 newtons of force, where a small arrow might indicate 5 newtons of force. All right, make sure that the sizes are accurate to what we're talking about. If two things are equal to each other, they should have the same size arrow. If one is bigger than the other, then it should have a bigger arrow. There is no certain number of forces required. You can either have 1, 2, 3, 100, it doesn't matter. So here's an example of what a free body diagram looks like. Sometimes we use a square to identify our object, sometimes we use a circle. It doesn't matter which one, just so long as we choose something. Then we take our forces and we point them in the direction that they're occurring. So right here, I can see that there's a force applied acting in the rightward direction, a force friction acting in the leftward direction, normal acting up, and gravity acting down. I can see the sizes of these arrows and that friction and applied are the same size. I can also see that normal and gravity are the same size. We're going to say that balance forces is what happens when these forces cancel each other out. So for instance, right here, since friction and applied are balanced, meaning that they're the same size, they're going to cancel each other out. We're also going to have unbalanced forces. And unbalanced forces are going to cause the object to accelerate in the direction of the stronger force. So if I had a bigger force applied here, it would mean that this was unbalanced, so my object would be speeding up to the right. Something important to note, though, about balanced forces is that they can mean two things. It can mean, one, that the object is at rest, or two, it can mean that the object is moving at a constant velocity. Just a quick example of what an unbalanced force would look like. Say I have friction acting to the left and I have force applied to the right. I can clearly see here that these forces are unbalanced. My force applied is huge compared to my force friction. So now what we want to do is we want to talk about some helpful hints for when we construct these free body diagrams. The first hint is that if we have an applied force, it's going to require direct contact. And what we mean by that is, for instance, let's say that we have a football flying through the air where it no longer has contact with the thrower. That means that any object that is in the air is not going to have an applied force on it. Again, The applied force is only present when the object is being touched. Number two would be that balance forces mean that an object is either at rest or moving with a constant velocity. This is the one that people always mess up on. So you need to remember that an object can still be moving when the forces are balanced. So number three is that a normal force always points up when the object is lying on a flat surface. So what we mean by that is, let's say that we have a table here and this table is flat. Therefore, if we had a box, the normal force is going to point straight upward. We can say that the normal force is always pointing up when it lies on a flat surface because the normal force really just points perpendicular to our surface. And perpendicular is referring to the normal force creating a 90-degree angle with our surface. So in this case, a flat surface would result in the normal force pointing up. But if we had a surface that was on an angle and had our object on that surface, our normal force would now look something like this. We can see though that this normal force is still perpendicular to our surface. Number four, which is also one of the most important things, is that gravity will always point down, no matter what, okay? So anytime we have an object, we always want to start with gravity and we always want it to point directly down. Now let's take a look at a few examples. So for example number one, we have somebody sitting at rest at their desk. When drawing our free body diagrams, we're always going to start with gravity. And gravity, just like we said before, points down. Then we're going to think, are there any forces acting in the opposite direction? Well, if we're sitting at our desk, it means that we're sitting on a surface. So therefore, we have a surface. Since we have a surface, we're going to have a normal force pointing perpendicular from that surface. In this case, that's going to be straight up. Are there any forces acting on us in the left or right direction? No, it just says that we're sitting there. It doesn't say that we're being pushed to the left or pushed to the right. It just says that we're sitting at rest. We know that all these forces are balanced because we know that we're at rest. And balanced forces, like we said before, refers to being at rest or a constant velocity. In this case, it's at rest. Example number two is us driving in a car at a constant velocity. So again, constant velocity is going to mean that these forces are balanced. Like we said before, we always want to start with gravity. Then from there, we need to think, well, what is our car driving on? Well, it's not a flying car. We're not there yet. So our car is driving on the ground. A ground is the surface. Therefore, we're going to have a normal force pointing up from that surface. Why is the car moving at a constant velocity? We can assume that the engine or something is applying a force that is pushing that car to the right or left. In this problem, we're going to say that it's applying a force to the right. And then we know that because this object is moving, it's also experiencing a force in the opposite direction of its motion. And that force is just going to be friction. We can see that all of our forces here are balanced, meaning that all of the arrows have the same size. Because they're balanced, we said it can mean one of two things, either moving at a constant velocity or at rest. We can see that friction and force applied are balanced here. And we know that the car is moving at a constant velocity, so it's moving at a constant velocity to the right. We know it's moving to the right because friction points in the opposite direction of motion. The other forces that we can see are balanced are gravity and normal. And if we're thinking about our car, we have two options here. Either it's moving at a constant velocity up and down, or it's at rest up and down. Well, I don't know about you, but when I drive my car on the road, it stays on the road. So therefore, since these two forces are balanced, we're going to say that it is at rest in the y direction, meaning that it's not moving up or down. Example number three, you are accelerating while driving your car. Well, here's our key word here, accelerating. And we already know that accelerating is referencing the fact that we have unbalanced forces. So let's go ahead and label our forces just like we did before. Always start with gravity. We have gravity pointed down. Again, this car is on the ground. We do not have those flying cars. I did just see an article though, and maybe if you're listening to this video 20 years in the future, we will have flying cars. But at the moment, the closest they have got is in Japan, where they produced a prototype flying car. And I believe they said hopefully that they'll have them up and running by 2030. Because our car is not flying, it's on the ground. Because it's on the ground and it's a surface, we have a normal force pointing up. Our car is accelerating, and our car is going to accelerate to the left or right. We're not given enough information to know which way, but for the sake of this problem, I'm just going to say that the rightward direction is where we're moving. Therefore, I'm going to have a big force applied to the right. Since my car is moving to the right, it means I have friction in the opposite direction. So I'm going to have a smaller force friction pointed to the left. It's very obvious that force applied and force friction are unbalanced because force applied is so much bigger than force friction here. Therefore, the applied force is stronger, which is what's making that car accelerate. Force normal and force gravity are both equal and balanced, which just means that my car is not moving up or down in the y direction. Here's our last problem. You are decelerating with your foot off both the brake and the gas pedals. So decelerating is just a fancy word for saying negative acceleration. Well, we see the word acceleration here, so that's going to mean, again, that we're unbalanced. Identifying our forces like we've done before, we know gravity points down. Again, this car is on the ground, it's on a surface, so we have a normal force pointing up because we're assuming that we're driving on a flat ground. If we were driving on a hill, we would have a different free body diagram. But for the sake of the problem, let's keep things simple and say that we're just driving on a flat street. So now we need to look at our problem and see that we're decelerating with our foot off both the brake and the gas pedal. This means that nothing is being applied to the right to move us. So therefore, we are not going to have a force pushing to the right anymore. Well, what's slowing us down? The only thing slowing us down in this case is going to be friction. So we're just going to have force friction pointed to the left. And since there's no other forces on the right side, force friction is unbalanced. We are decelerating because our force friction is unbalanced. And like I said before, there's no applied force, so the only force acting on this object in the x direction is friction, therefore making our car slow down. So if friction is acting in the opposite direction of motion, it's going to be slowing my car down. Just to summarize what we talked about, when drawing free body diagrams, make sure you're identifying what forces are at work in your problem. Always start with force gravity. Then from there, think if you have a surface. If you have a flat surface, then you know that you have force normal. If you don't have a surface, then you don't have force normal. If your object's moving, then you have force friction. And force friction is going to act in the opposite direction of motion. If your object is being pushed or pulled, then you'll have a force acting in that direction as well. If your object is just moving with no forces being applied to it and it's slowing down, then you will only have force friction acting in the x direction. Again, just make sure that you're reading the problem carefully and you're identifying whether that object's on the ground or in the air. Because if the object is in the air and we're ignoring air resistance, then the only forces that can act on an object in the air are gravity. And that's because gravity is a distant force where it doesn't need to be touching the object for it to impact its motion.